Okay, now as usual, was a review. I didn't quite, last Wednesday, no matter what lecture I have on tape or not, we were talking about the properties of wave functions. Remember that wave functions, and today we're going to talk about operators, so remind you about wave functions. Wave functions are models of things. The thing that we're going to be sticking with for the next 2 weeks is an electron by itself in an empty universe that goes on forever. Weird, unrealistic, but very easy to understand. We often call that the free wave. It's in quantum mechanics with the free wave, it's the free wave problem. So you'll always hear me talking about a free wave. So listen to that from now on, free waves. That's sine, cosine, e to the ix, e to the minus ix. Those are all free waves. I'm going to tell you a little bit more about e to the I to the x, e to the minus ix. We're going to talk a lot more about that today. Okay, those are models of things. We're going to do electrons. And then we're going to do quantum mechanics on them. They are designed to incorporate the de Broglie wavelength. That's their purpose. You know, when Heisenberg and Schrodinger realized that matter needed to have wave-like properties, they realized, okay, my model for them must have a wavelength associated, a de Broglie wavelength associated with it. It must have lambda equals the Planck constant divided by the momentum. Where is that? My model must have that inside of it. And so they have wave functions, and they're often sines and cosines. And then we'll talk more about operators. Now, Born came along, and you know, people at first, and even today, still say, debate, that wave functions have no meaning, that the model is useful for getting energies out, but the model itself is just a mathematical construct that itself is meaningless. So, so that's to say matter does not have a wavelength. So, but we're pretty sure that's not true. Okay, so people sometimes debated, what does a wave function, does it even mean anything, or is it just a mathematical tool that by itself is actually meaningless? It just has a useful property. Born said no. Born said that the wave function squared is a probability distribution. Okay, that's great, but to normalize it, you have to do this. Now, as you're going to see a bit more today, and then definitely as we go further, remember that we often do not use the Schrodinger equation to solve the Schrodinger equation. That's the thing I hate about this. That's so freaking weird. But it is true. So, when it comes to free wave, that's an example. It's sine or cosine. Sine or cosine. It's a wave. I plug it into the Schrodinger equation, hey, it works. I figured it out after the fact. Okay, but sine and cosine are not normalized. So you often figure out wave functions based on horse sense, but then you have to normalize them. We did not run into that in Maxwell-Boltzmann because the Boltzmann distribution that we started out with had a normalization factor. It had something in the denominator that normalized it. When you come up with a wave function, it's not normalized, and so you have to remember to put that part in, or everything else will screw up. Now, we also talked about the properties of wave functions, and I got through 2 of them. Here's the other 2. Not zero everywhere. Remember, that's basically the null solution, which is, the idea of this is that that's meaningless. And I'm telling you, it actually isn't, and you'll actually see some examples of that, so I don't know why this is traditionally included. I want you to know that people generally say this, but it's not really true. And when it comes to our unrealistic but easy free wave model for you to understand quantum mechanics, cosine over the integral of cosine squared. Cosine squared is always positive, so if you integrate from infinity to minus infinity, what's the area? It's infinity, right? So that's a weirdo. Now remember, it's unrealistic. Now that would technically make the normalized wave function 0 everywhere. But now it does have, as much as that's funky, it does have an interpretation. If a particle can be anywhere to the left and right of center, how far? Infinitely far, left and right. What's the probability it's in a particular position, any particular position? What's the probability it's 1 mile to the right? When it can be infinitely to the right or infinitely to the left. What's the probability that it's right there? 0, right. So it actually makes sense in the case of a free wave. And as I mentioned to you, what people, when this class is taught, what people try to do is everyone starts with free waves because it's crazy not to. This gets way harder after you do free waves. But what they try to do is not allow you to realize the normalization constant is technically infinity. It's 1 over the square root of infinity. People try to get you to not notice that. Just like you guys gotta remind me of that. I forget that every time. Okay, so just saying. Okay, smooth and continuous, just, that's a big one. That is a big one. This one's always right. Now remember that what you have, if you have like a sudden jump, like no, that means that you have kind of like 2 probabilities to be in the same position, and no, you know, people say, oh, quantum mechanics is so weird and there's so many strange, the cat's alive and dead. And that's wrong. And number 2, it's a probability, it's the mathematics of probabilities. And no matter how weird quantum mechanics is supposed to be, you cannot have 2 probabilities to be in the same place. No event has 2 probabilities. That's always true. So you cannot do this. More importantly is this one. So this is continuous, this is smooth. This is not smooth, it has a cusp. And as you're going to see more and more, actually you already know enough. You already know enough that the double derivative of a wave function is related to its energy. If you have a cusp, you've got infinite energy. So no, you can't do this. This is a very big deal. Okay, double that. Don't worry. Same thing as this one here. Remember, if you integrate the wave function squared over some region, you would technically have 2 potential solutions. The area here is 1 probability, but then the area to here would be another probability, and then the area to here is like a 3rd probability. No, that just doesn't make sense. Don't worry about this one. You don't really want to run into this one. This last one is huge. Okay, again, big deal. Energies make sense. Big deal. Those are the 2 big deals. Notice I didn't draw anything. Okay, so let's go ahead. I'm going to start to move away from free waves. You're going to see a couple more quantum mechanical paradigms, that means examples, beyond free wave. I'm going to start introducing them to you. What I'm going to do is take a free wave but put it in a box, often called a particle in a box. Now to do that, I'm going to create some kind of potential trap, such that to be to the left or to the right, actually I'll call it 0 to L, if this particle is to the left of 0 or to the right of L, the energy of this thing is infinitely high. So maybe it's an my free wave is often an electron, and maybe the potential barrier is like a voltage. It's like an electrostatic field that would drive the energy to infinity if it's left or right. Okay, so whatever. Okay, here's the thing. Let's take the middle part of a cosine, right? Put it here, or actually that's kind of like more like a sine, given where I've given the symmetry. But anyway, what if I did this? Is that okay? What do you think? Doesn't fit within the bounds. It doesn't fit, but why should it? Why should it fit in the box? It would have infinity what? So remember that this is a probability distribution. Let's say that I just drew the wave function squared. In this case, it's kind of a bell-shaped thing, right? So if I drew the wave function squared, it basically looked the same. So there's a certain probability that it's located left of 0 and right of L, right? All right, so what's the energy of this particle? For it to exist in an infinitely high energy part, how much energy does it have? Okay, how much energy is there in the universe? It's finite. I don't think it's infinite. No one thinks it's infinite, but I don't think this particle has it. Okay, so here's a good solution to this. So no, that wave function doesn't work. And now this is part of point number 4. The waves have to have sensible energies. Now that means that you have stipulations on the wave functions. Again, I'm still talking about wave functions. That means that this is okay. That's okay. You see how it tapers off to 0? So, there's a little funkiness to what I've drawn here. I've drawn two graphs. I've drawn an energy graph, and I'm also drawing a wave function graph. So when I said that this is 0, so this part is for energy, and then maybe this part is for the wave function. So be a little careful of that. I'm often drawing what I would call a potential energy surface on the graph, and then I draw a wave function on the same graph, but those are two graphs that are overlaying each other. So this is okay. This is okay because the wave function is tapering off to 0 here. So on this other axis, that's 0. That's okay. That's okay because it doesn't have any probability amplitude in this infinitely high region, and to do so, it would have to have infinite amounts of energy. Okay, so that's a restriction. The wave function has to look like this. Now let me give you another one. Is that okay? Huh?
Is it a negative energy?
Wait, no, hold on. Now, remember that wave function, the only thing that has any meaning is a wave function squared. So I've drawn it symmetric about 0, but does that mean anything? Besides, now it exists between 0 and L, and between 0 and L there's no energy. It tapers off to the left of 0 to 0, tapers off to the right of 0 to 0. So is this okay? Yeah? Well, I mean, I'm just drawing a wave function. So now the interpretation of the wave function needs to be squared, but regardless, to the left of 0, to the right of 0, itself or squared is 0. Is that okay?
Sure is.
Okay, what about this? What about this guy? What if I spread it out a bit? Yeah? That? No, that's not okay for the same reason. The same reason. Now there's some finite probability of being left or right of the potential trap. For it to have some probability, and I didn't draw much here, I exaggerated a little bit last time. For it to exist outside the box to any small extent means that there's some probability it's to the left or right of L, and that requires infinite energy. Even a small part of it. If a small part of it is left of 0 or right of L, then it has to have infinite energy, which is not sensible. Right? So you're okay with this? Yeah? All right, it's really simple. The wave function has to fit in the box. Because if it doesn't, the energy is infinity. It's just that easy. Okay, but notice something. So I can't draw any wave function, right? I mean, I can't draw this. In fact, here, now I'm gonna redraw this, and I'm gonna stack the wave functions on top of each other. Just understand that that they're 0 at the bottom. So I won't put any kind of labeling on the right axis. Okay, so this is okay. This is okay. This is okay. All right, see all that? Those are all okay. Because I have them going to, they hit 0. I'm not drawing it perfectly, but they hit 0 at the sides. Those are all okay. Right? But any of the ones in between are not, because they'll leak out. They won't be 0 at 0 or 0 at L. Okay, now guess what? You know enough. If I can model, see, I could probably, that's like a sine function, right? And that's like a sine function with a node. Is that right? What if I was to do this? What do you think if I took those functions and I did this to them? What would I get for here? Now you recognize this, right? You know what this is? Right, that's kinetic energy, right? Remember, we saw this on Monday. Okay, this is kinetic energy. What do you think the energy of this is? Well, sorry, you don't, I mean, I have to put numbers here, so that's ridiculous. But This guy has a certain energy, right? It's related to the curvature. Remember that a double derivative is the curvature. How does the curvature of this guy compare to this guy? Is it curvier?
No. Yes.
Yes, this is way curvier than this. It is way curvier. There can't be two loops when there's only one without being curvier. Okay, and this one?
That's more curvy.
More curvy. Okay, so this has 1 unit of kinetic energy, this has maybe 2, and this has maybe 3. They have different energies. Okay, now again, if this is 1 unit of kinetic energy and this is 2, can I have 1.5 units of kinetic energy? Could I do that? No, because it wouldn't, because to do so would require me to draw a curvature that doesn't fit in the box. Right, so if I wanted to do 1.5, here, let me draw that here. If I wanted to draw 1.5 units, it might look something like this. Right, see what I mean? I'm taking this guy and I'm kind of squishing it down a little bit so that it's more like that, but not quite. You see that? So this is 1.5 units of curvature, which is kinetic energy. It spills off to the right. It can't do that. So, you can see that there's only certain wave functions fit in the box, and the energies come in steps, 1, 2, 3. They're quantized into discrete values. Now, for 1,000 points, guess where the word quantum mechanics comes from? This is the origin of the word quantum mechanics. Because when you start doing more realistic problems, like instead of the free wave, again, that's hideously unrealistic, but easy. When you start doing more realistic things, like, I don't know, like the universe is finite, or the electron might hit something, the electron in outer space, if it goes far enough, will hit something, so that there is a finite amount of distance it can travel before it hits something, which is true. What you find is that it can't have any energy. It can't have any kinetic energy it wants. Otherwise, it'll penetrate into the barrier, which would require, in this particular model, infinite energy. All right with that? Okay, so anyway, and what's going to help is, you're going to see this a zillion more times. Okay, now getting back to this, let me start there, because I'm actually not using time too well, because today we're talking about, I can spell, eigenvalue equations. Okay, so you've already seen this. I'm giving it a name, but let me back up there. Okay, now let me just do some pure math. Let's forget minus h bar squared over 2m and yada yada yada. Let's do this. Now, if we were in math class, if we were in different diffie-q, we'd see this. Okay, now notice this is very similar to this is actually very similar to the Schrodinger equation. I'm just missing an h bar squared over 2m. Anyway, let's just take a step back. Let's go to math class. Let's go to diffie-q class. This is a constant, that's a double derivative. If you were in diffie-q, you would see this, and then you'd say, hey, solve this. My question to you is, what the hell does this even mean? Right? Now, I think you know this is a double derivative, so you know what that means, and that is a constant, so it could be phi or pi or Planck's constant. Okay, so now, all right, but what? Because this by itself doesn't equal 5. It's a double derivative. It does things. This is a number. It doesn't do anything except represent 5 of something. Maybe it's cats. Anyway, what do I do with this? Okay, maybe you can apply a function. What function can I take the double derivative of to get 5? X squared. 5x is, the double derivative of 5x is 0. 5 halves x squared? 5 halves x squared, the double derivative would yield 5. Okay, now my question, all right, so Smiley pointed out, I actually know all your names, but anyway, Smiley pointed out that if we're in math class, and it's like, what do you do with this? If the answer is, well, you write this, and you've solved it. Because I told you that C was 5. That's true. That is true. And really nothing else would work. But now let me ask you this though. Do you think that's really what's happening? No. Any idea? So what it is you're being asked to solve this. That's what you're being asked to solve. This is the correct mathematical expression for what is technically the easiest second order differential equation that exists. This is what you're looking for. Now you've already seen this, I'm just giving it a name. Remember that I said to you that when you're doing quantum mechanics, now remember we talked about the derivation of the kinetic energy operator, which is a double derivative times some constants. This gives us the de Broglie wavelength, right? The whole point of momentum squared is that it gives us the de Broglie wavelength. Now, if I'm going to translate this to quantum, this is what I put. And the solution, of course, is to write a wave function. But just like in diffie-cube, you have to put it on both sides. So while I'm perfectly capable of taking the double derivative of something, where this turns into, to be blunt, I know I shouldn't be using this language, where this turns into a hideous nightmare is that the double derivative of the wave function has to be a number times the wave function. And that introduces a layer of complication that can be mind-blowing. Now, not so much with this example. Remember, there's no potential energy. That's where it gets hideous, heads up. This is not too bad, because sine, cosine work. Double derivative of cosine is minus cosine. Oh, look, I got a minus sign there. Double derivative of sine is minus sine. Again, I got the minus sign there. So we're okay. We're okay now. That's why we do free waves at first. Remember that e to the I x is also going to work. We're going to do that right now, in fact. When I add potential energy, this is going to get nightmare. So just heads up. So again, this is why we do free wave. Okay. Now, the way to express this mathematical thing, we call it an eigenvalue equation. Now, I'm gonna put it like this. Okay, this is an operator. Okay, and an example of an operator is this. That's an operator. It acts on a function and it returns a number times that function. Okay, this is a number. Okay, let me be very mathematical. A scalar. Some of you, maybe if you are kind of a math crowd, right? So that's a scalar or a number like 5. It's also called an eigenvalue. And the psi is an eigenfunction. Now, eigen is German for, I believe it's the same. So that's the idea. You can operate on the wave function, and that usually means taking a derivative or a double derivative, and yet the wave function, the eigenfunction is the same. You operate on the eigenfunction and you return the same function, which again in German is an eigenfunction, the same function. And again, not terribly hard right now, because double derivative of cosine is still a cosine, but when I start throwing in double derivative plus, double derivative of x plus x, you can imagine, oh, that really does get way harder. So anyway, heads up on that. Okay, now you have seen, this is the kinetic energy operator. So it turns out we have all kinds of operators. So I'm going to go ahead and tell you what some of them are. Well, here, I'll actually start with momentum, which guess what, is basically the square root of that. And I've got the square root of a minus sign, so what that is h bar over I. Okay. Now when I square that, I get minus h bar squared double derivative of x. Kinetic energy, of course, sorry, let me do momentum squared. Yeah, why don't I just write it down, right? That's way easier. Okay, that's kind of brainless. Now, kinetic energy is easy because it's p squared over 2m. Mass is something that has to be given to you. It's not a fair, you know, I can't say, oh, solve this crazy problem with quantum mechanics. And I can't just not tell you what the problem is. I have to provide certain levels of information about what it is I'm trying to model via quantum mechanics. Part of that information would necessitate knowing the mass. Okay, so, yeah, there you go. There you go. So, yeah, so what I'll do is, these are just 3 examples. Sorry, little equal sign there. These are 3 examples. There are operators for everything. But of course, everything not like, how do you feel, right? That doesn't make sense. For things that are physical. Momentum, energy, potential energy. Here's a good one, angular momentum. Yeah. 1 month we're doing angular momentum. That's a tough one. Angular momentum actually is a 3-dimensional vector, so we can ask for angular momentum in the x, y, and z direction. So there's operators for all of those. There's really nothing that's physical that we don't have an operator for. We have operator for everything. And they're usually not too hard to figure out. Like it wasn't terribly hard to figure out momentum squared. The de Broglie wavelength gave us that. And I just take the square root, and then I get, and then I got momentum. So there's ways to figure these out that really aren't terrible. Okay, now what I need to do is operate on wave functions, and then get the eigenvalue times that wave function. And the eigenvalue, guess what? If I operate on the eigenfunction with the momentum operator, and I get 5 times the wave function, what is 5? It's the eigenvalue of the momentum operator. So it's 5 what?
Meter squared per second.
It's the momentum. It's the momentum. If you operate, and units would work out. I'm being a little fanciful right now. So if this is the momentum operator, times its operates on the wave function, it'll return the momentum times the wave function. If it's angular momentum in the z direction, right? Wave function, you get the angular momentum in the z direction. It's now a number. It's a number now. It's like 5 or units. Anyway, operators tell us things. That's the whole point. Wave functions are models for things. Operators tell us how to analyze the model for their properties, like angular momentum and kinetic energy and potential energy and all that jazz. Okay, so best now to spend the next remainder of our time, I'm actually just going to do example after example after example after example. And we're also going to do some practice with imaginary representations, imaginary mathematics, because more and more you're going to see why, as much as maybe some of you, I mean, you should have seen this before, but if you haven't, you're going to learn it. And it's just, this is going to be way, 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 way easier. Okay. So what I'm going to do first is I'm going to do kinetic energy. I'm going to do kinetic energy on cosine. Now remember that let me back up. Okay. Last question on the exam. The universe has an electron and nothing else. The universe goes on forever. You know that, what am I doing? Let me check. You know that sine or cosine works. You just know that. Okay, on the exam I would tell you. All right. The universe has an electron, the universe is infinite. What's the kinetic energy? All right, so there you go. Now you should know that the wave function, and I won't leave you hanging like that on the exam. Of course I'm going to tell you that the wave function, I'm going to do, instead of cosine, I'm going to do sine. So we're going to have some normalization constant, sine of kx. I could have done cosine, I'm just not. I just feel like doing sine, because they're both fine. Okay. Now, we're going to apply the kinetic energy operator to that, and there you go. But I'm going to do this in the complex plane, because I want you to get used to that. Okay, so now what I need to see is I'm going to operate on this with the kinetic energy operator, and I better get the energy out, the kinetic energy out. Now notice that I've used a different symbol. So hold on, let me write this down. Energy operator. Okay, it turns out that when our operator is that of energy, it's special. It even gets a name, Hamiltonian. Energy is special. The energy operator is special. It's different than momentum, angular momentum, position. There are like, I've seen a textbook with all the operators that are known, there's like 1,000. But the one that is energy is special. It even gets its own symbol, an H, which is not hard to figure that out, all right? So, and it gets a little hat. The little hat means operator. Okay, so look out for that too. Again, lingo that I can't avoid. Okay, so I'm gonna do kinetic energy on sine, but I'm gonna do it in the complex representation because later on you're gonna see that this is gonna save you infinite amounts of time. You're gonna do things in 2 or 3 steps as opposed to 20 when you do it that way. H bar squared over 2m. If you forget that this is not the hard part. I won't go nutso on you if you occasionally forget the minus h bar squared over 2m. Remember, those are just numbers, they're scalars. Okay, so I have some kind of normalization constant, and now I am going to put this in the complex representation. And I'm going to simplify it as well. Okay, again, now hopefully, if you honestly did your homework, or you recall some of your calc and you should have seen this before, that is a sine function. You've seen that a zillion times now. Normally you just write e to the ikx minus e to the minus ikx over 2y, but I just factored it, just to make it a little easier. Okay, now what? All right, so let's do the first derivative. First derivative, so there's going to be one derivative left. And let's see here. Okay, the first derivative, what's the derivative of ikx? Ik. Huh?
Wait, what
Ik, and the derivative of e to the ikx, I heard ik. Right, you see, it comes back. That's why e to the ikx and sines and cosines are incredibly useful. Okay, and then, so we don't go through that again, let me just write it down. Notice that I had two minuses. Notice that? Now, you may be tempted to simplify it further. Don't. Just wait. Just wait. Look out for that. Finish the operation before you simplify always. Okay, now, okay, what's now what? Ik e to the ikx. What is it?
I squared, a squared.
There you go. What's I squared? Minus 1. Let me make sure. Yeah, minus k. Okay. Ikx. Okay. Now I have to admit okay. Minus I squared k squared is yeah. Plus k squared, right? I feel like I've done something wrong here. No, I haven't. There we go. Now, the reason I didn't want you to simplify it, you notice that you could have gotten rid of the i's or something or done some factoring. Don't ever do that. For the reason that's being made apparent right now. Sorry for my pumping to the board. Okay, now what? Okay, so this is my h bar squared over 2m. Now I'm going to factor out a k squared. And let's see, what have we got left? We've got n. Okay, I've got e to the, I'm going to actually factor out a minus sign. This is a little funky. What I've done is I've factored out minus k squared. I factored out minus k squared. Notice that because that's now positive. And that means that this is e to the ikx over 2i minus e to the minus ikx. Okay, there you go. All right, you see it? You see it? Where's the eigenvalue?
H bar squared, A squared.
Where's the eigenfunction? Where's the original function? Is the original function back sine kx? Do you see sine kx?
Yes.
You see n sine kx, right? Okay, so therefore, the Hamiltonian operator on the wave function returned h bar squared k squared over 2m times the wave function. Is that right? Is that what just happened? Huh?
Sounds about right.
Yeah. What happened that happened right in front of you? That's what I'm asking. What happened is reality, which is this. Okay, so what do you think this is? All right, so that's the eigenvalue, but what is it?
Oh, it's the energy.
It's the energy, kinetic energy specifically, right? Because we don't have potential energy. If I had some potential energy and I dealt with that, then it would be total energy. But this is a flat world. Remember, this is an electron in the universe by itself. There's nothing to have potential energy with. There's nothing else there. There's no potential energy. So the kinetic energy is the total energy. So this is the total energy, or kinetic energy, which is the same thing. So there you go. You have wave functions, you have operators, you operate on the wave functions to get answers to things that you could reasonably ask. You can't ask it how it feels, right? But you can ask its energy. So there you go. All right, now I'm going to do something that, to a large extent, you're going to really hate this. This is where things go off the rails hideously. So you see that I bet you think you get it. All right, remember, Hamiltonian, if the operator is the energy, then it gets a special H. Okay, let's now, an electron all by itself, the wave function is a sine, and I can get the energy. Great. Okay, what about its momentum? If I get its momentum, I can know whether it's going like left or right. Positive momentum would be right, and negative momentum would be left. So there's value. You'd be thinking I could just take the square root of that. I can take the square root of that, but what's missing is momentum is directional. So if it's positive, it's moving right, negative, it's moving left. So I can't just take the square root of that and get the momentum. Remember, that's momentum squared divided by 2m. I can't do that. I need to use the momentum operator. So what is the momentum? Let's use the eigenvalue equation and see what we get. Okay, so that's h bar over I, derivative of n. I don't think I'm being consistent on my bracketing, but okay, yeah, this is a sine. So we can actually do this in one step. Let's see, you got h bar over I, n I k x over minus plus ikx. Sorry, I'm having to do this in my head. And actually, I need to do one more algebra. See if I can do a little algebra because I'm not seeing the wave function. So I have a little bit of a problem. I don't quite see the wave function. What do I want to do? I want to factor out an I and a k probably. So I got h bar k. So I factored out an I and a k, so I expect you to, you can hack that, right? N. Wait, no, but, right, just ik. Sorry. Okay, so I factored out an I and a K. So I end up with e to the plus e to the minus ik. Okay, there we go. Okay, so where's our eigenvalue? Eigenvalue and eigenfunction.
The eigenvalue is the H bar K.
Okay, what do you guys think? Eigenvalue?
No,
Oh, I
No?
see. Some.
it's not the same function.
Eigenvalue?
No,
Cos of hk is moving to the right because it's positive?
no, it's
Eigenfunction?
No.
No. This is a sine. Anyone know what this is?
cosine.
The derivative of sine is what?
Cosine.
Cosine. So this is h bar k cosine. Okay, let's see what we got. Let's summarize this. Summarize it. P, momentum operator on sine gave h bar k cosine. Okay, again, this is the part you're going to hate. So what do? We do not have an eigenvalue equation. This is, remember, eigenfunctions means the same functions. That means the same function on the left and right, but sine is not a cosine. We do not have an eigenvalue equation. This failed. So what do we do with the h bar k? What do we do with it?
If you multiply by something that makes it sine.
By itself, this has failed. If anything else I do to it, I'm monkeying up the, I'm changing it, but I'm not supposed to. Any ideas?
Multiply that.
So you're actually trying to solve this, but here's the solution. You don't. It's all wrong. It's wrong. Everything I did was wrong. The reason is that sine is not an eigenfunction of the operator.
So
It's fundamentally wrong to do it this way. I was wrong before I even started the question. Operators have to operate. Here, I gotta write this down. And we're almost ready for a break. Eigenfunctions, Friday. Operators must operate on their functions. Okay, sine, cosine are cool with the Hamiltonian. They are eigenfunctions of the Hamiltonian operator, the p squared operator. It does not mean that they are necessarily the functions of the momentum operator. Even though the kinetic energy operator is the momentum operator squared. That's different enough. I mean, it's not the same. It's composed of it, but it is not it. This is the part I'm telling you slays people on quantum mechanics. When I've got the Hamiltonian and I've got wave functions, I know your instinct is, okay, well now I know everything. No, you know the energy. You know the wave function and you know the energy. That's what you know. It is not necessarily true that you can then use the other operators on those wave functions. It may or may not be true. Now, if this happened to pass muster, if I was able to take the derivative of this and it comes back to life, then I would have been okay, and the eigenvalue would have been the momentum. But it did not pass muster. It's all junk. It's mathematical noise. The way I have to solve this is I have to feed the momentum operator its wave function, which is not the same wave function as the Hamiltonian's wave function. They're not the same wave function, which, as you're seeing right now, turns into an absolute nightmare. Now, let me show you real quick one way to solve this, which is, let me give you an example of how you get around this, and then we're going to do something very different in the next hour. Okay, let's do this. Now, remember that remember I was telling you that when it comes to the free wave, sines and cosines work for kinetic energy, for the Hamiltonian. They obviously work because the double derivative of sine is sine. Anyway, let's try e to the ikx. Right, let me just do it. H bar squared, k squared over 2m. Did it pass muster? Did it work? Yeah? Okay, let's do, okay, so e to the ikx is an eigenvalue of the Hamiltonian, just like sine and cosine. Let's do minus ikx, and what do I get? And it's a little harder because now you gotta do a minus sign. You're gonna get a minus sign times a minus sign, by the way. Same thing, right? If you're having a little trouble, just work it out because you should be able to do this. An easy way to think about this is that the minus sign from here to here, you have a minus sign that just comes down twice. Well, that doesn't do anything, right? So you get the same thing. Okay, fine, sure. But now, let's do the thing I told you was a problem. Let's do momentum. We'll just do right wave. And you may be wondering why I call it right wave. That's because did it pass muster? Is it an eigenfunction? Yes. What's the eigenvalue? Right wave or left wave? Is it moving right or left? Right. Right, it's moving right. Here, let's do momentum on left wave. Right? There you go. Huh? Yeah, right? Now, I'm calling it right because momentum is directional. That's a positive number. Do this guy. It's negative. That means it's moving left. Okay, so free waves. Sine, cosine, e to the ikx, e to the ikx, e to the minus ikx. Those are all valid wave functions of the Hamiltonian. However, only two of them are eigenfunctions simultaneously of momentum, and that's e to the ikx and e to the minus ikx. Those are eigenfunctions of momentum. So you can be eigenfunctions of one operator, but not the other, or you may or may not be. And there you go, there's the answer. Now what's interesting is a particle by itself in the universe is probably only, in a one-dimensional universe by the way, if we're only doing x, is either moving left or right. And if I know that, if I know it's moving right, I know that's the right wave function. If it's moving left, that's what's telling me. God, if it's moving left, that's the right wave function. If I tell you there's a free electron in the universe that's moving to the right, you at this point should know that's the wave function. Again, notice you didn't use the Schrodinger equation to solve that. We just figured it out by other means. If it's moving left, that's the right wave function. Okay, now let me give you a hint about the next lecture. So what the hell are sine and cosine then? Now these guys, now you see why I like e to the ix? It's so easy. Right, left. But sine and cosine are valid solutions too, at least for the Hamiltonian. What do you think their momentums are? Now note that I can think of three possibilities for this free particle in the universe by itself. It's either moving to the left, or moving to the right, or what's the other possibility?
Not moving.
Not moving. What do you think sine and cosine correspond to?
Not moving.
Just say it again. Not moving. Sine and cosine are for the particle that happens to be stationary. And how do I know that? I'll show you how to solve momentum for sine and cosine. You actually can do it, and it's a crazy mathematical trick. It can be done. So we're going to do that in the next hour.